Hi, in this video we're going to talk about curves defined by parametric equations. The reason we need parametric equations, the reason we find them useful, is because they help us describe motion. Useful because they help define or describe motion. Now, you might be thinking that in physics we used equations all the time that describe motions, or in our previous math classes, something like 16 minus t squared describes an object thrown in free fall just fine, right? And we had a parabola. But these were inadequate in some ways. Explicit equations and implicit, both explicit and implicit equations have issues with truly describing motion. So one of the issues would be that explicit functions, like the one above, have to pass the vertical line test to do everything we want to do with them, right? We can't have a function that is a circle, right? So circles are out. Circular motion, out. And you might be thinking, well, okay, but for a circle, we could just use an implicit equation, like x squared plus y squared equals r squared, right? That's an implicit equation. It implicitly describes x in terms of y. But either way, both implicit and explicit cannot show an orientation. You can say, oh, well, we're going around the circle in a counterclockwise way, but there's nothing in the equation that will give us that. So that's what we'll use parametric equations to do, is we'll fix both of these problems. We won't have to worry too much about the vertical line test, nor will we have to worry about, well, how can we talk about orientation? Do I just have to know it? No, we'll be able to get this out of the equations themselves. So the parametric equations will usually look like this. Equations. They have x equals some function of t, and y equals some function of t. Sorry, some other function of t. We'll use a different letter, like g. So the idea is that each equation is a function of t. So each variable, rectangular variable still, is a function of t. And this t, you might be able to guess, represents time. Usually in some interval. Interval, like a to b. I guess I want to say it can be infinite. But usually it'll be in a closed interval a to b. And if the interval has endpoints, we will call them the initial point and the terminal point. So at this point, it might be good to see a little picture of what we're talking about. I mean, before we even get into an example. So we have our normal XY plane, and maybe I'm trying to trace the path of an ant as it crawls along my computer screen. So again, this ant might go back and forth and all over the place, right? So this path, and it will go in a direction, right? We have a clearly defined direction because the ant is traveling along time. So one more time, this curve doesn't pass the vertical line test, right? We have that issue. We're going to solve that because we don't have to worry about the vertical line test for the graph, because each coordinate, looking up here, each coordinate is a function by itself, but it doesn't mean the graph has to be a function anymore. The graph does not have to represent a function of y in terms of x. So we have this kind of a situation. I'm just going to make this a little clearer. That was an arrow, whereas these are endpoints. So we're saying it starts at some place t equals a, ends at some place t equals b. Because we know it starts, this is the start or the initial point, and this is the end or the terminal point. Now, just to be clear here, the coordinates of the graph, right? This graph has coordinates that look like x of t, comma, y of t. So notice that the coordinates now are functions, not they're not going to be just numbers anymore. The coordinates are given by these functions grouped into the normal xy system. So that means, for instance, like the initial point would be something like x of a, comma, y of a, plugging in that value of t into both of my functions. Or like f of a, comma, g of a, if we had that relationship described up top here. And the terminal point is x of b, y of b. Or again, f of b, g of b, if we have that relationship where we know what the functions of y, x and y are. So let's do our first example. X equals t squared minus 2t, y equals t plus 1, and we're going to describe the motion along this interval. Okay, so I want to be clear here. In the terminology from the previous slide, what we're talking about here is like f of t would be t squared minus 2t, g of t would just be t plus 1. Okay, that's what we're saying. These are functions of t. And this would be a, and this would be b. So one strategy that's helpful but slow is to make a table in order to graph it. So our table would have a t row, and the book has like an x and a y. I'd rather make it x comma y. I'd rather have this interval, I'd rather have it represented as a coordinate already so I know what I'm going to do when I graph it. So for something like -1, we should get x equals, so when t equals -1, I'll write it down here, just what we're writing in blue here, is -1 squared minus 2 times -1, which will be 1 plus 2, which will be 3. And y equals -1 plus 1, which is 0. So we're going to write this in the normal ordering, 3, 0. And what we find here, it's still a y-intercept. So what we find here is it's still an x-intercept. It's still an x-intercept. We still have the y-coordinate 0 x equals a number, that's still going to be an x-intercept. Again, even though t is not 0, that has nothing to do with intercepts. The t variable is independent. And you could go through and find the rest of these. And I think it would be a good idea to pause the video and try to find the rest of these to check that you understand how we're getting the coordinates. So here I go. I think it would be a good idea to pause the video here and try to find the rest of the coordinates. Go ahead. I will fill out the table myself. 3, 2, 1. All right, so let's check your answers. Here I'm getting 0, 1. Here I'm getting, oh boy, -1, 2. Here I'm getting 4 minus 4, 0, 3. 2 y-intercepts, notice that. And here I'm getting 3, 4. So what does this graph look like? Now when we're graphing, we only have an x and a y. There's no t-axis, okay? In a multivariable calculus class, you might end up with a third axis here, but even then, it usually won't be described as t. T is just some extra variable that's allowing us to describe this motion with the orientation, like I was saying. So 1, 2, 3. There's 3, 0, 0, 1, -1, 2, 0, 3, and 1, 2, 3, 4. And what the path looks like is a parabola. Now, if you don't see that from the points, we're going to have another way of talking about this. But again, I want to point out this is the terminal point. And this is the initial point. And we can notice this is definitely not a function of x. This is a function of y. But again, the other thing we have is this flow of time. Because this was t equals -1. This was t equals 1. And here we had t equals 3. Sorry, that's a -1 there. So we have that orientation, and we should usually express that with arrows on the curve. All right, so if that was too time-consuming, and if you still didn't see that shape, we usually can solve, this is important, we usually can solve for t in one equation and substitute to actually find a function. So how are we going to do that? If we look at our equations up top, if we look at our equations over here, we have one that's a lot easier to solve for t, the y coordinate, the y equation. So going back down to the bottom here, I'm going to have t could be described as y minus 1. And again, we had x equals y minus 1, or sorry, that's jumping ahead, t squared minus 2t. So if I combine these two equations, I get something like, I guess I'll do it, tx equals t squared 2 times t, and we're just replacing those t's with y minus 1, which should simplify to y squared minus 4y plus 3, which is a parabola in the x direction, opening in the x direction, because the coefficient here is positive. The coefficient from y squared is positive. And if you factored it, you would find it has those roots. It has 2 y-intercepts at +1 and +3. and you would get this, and you'd be able to graph it a lot faster this way. And that's usually how we'll end up graphing. Okay, so let's do another example. What if we had x equals square root t, y equals t? Now, the first thing you might notice is there's no domain listed for this problem. So in that case, if no domain listed given for t, use the natural domains. And when we say natural domain, we always mean just the normal domains of the functions. And I guess it would be the intersection here. I'll point that out for you. It'll be the intersection of the natural domains. So, right, this y has all real numbers. The x is the one that's restricted. So in this case, our t would have to be positive or 0, non-negative. Right, so you can go try to graph this if you wanted to. I'm going to take the other tactic, which is to say I'm going to solve this for t first. So let's just solve this for x. Sorry, let's solve the x equation for t. So it would be x squared equals t. And then when you combine that with the y equals x squared. Now, the reason I did it this way is to point out something very important. I know what this would look like. I know what y equals x squared looks like. It would look like this. I'm going to graph it in a dashed line for a very specific reason. So something like that. But again, whenever we're squaring both sides in a square root, we have to watch out. This is a very careful situation. T could only be positive from the very beginning. So t can only be positive, which means, I guess I'll write this, since t must be positive, x had to be positive. Like when we think about how x equals the square root of t, the outputs of that square root function had to be positive. So we only want the right half of this parabola. It's only this half, this parametric equation. And again, we have an orientation, which you should show with arrows. I will still say that the initial point is 0, 0. So one more time, we know the t has to be greater than 0. I can find the initial point, and then again, I'm kind of deriving the orientation from that. If you weren't sure about the orientation, you could test points and solve it that way. Okay, so there's 2 examples. Careful with your domains. That's 2 examples of equations where the strategy will be to solve for t and then substitute, okay? What if that doesn't work out so well? So an important example in parametric equations is something like this. And this is a really important example, super important. Make sure you understand what's going on here. If I have x equals a cosine theta, y equals a sine theta. All right. A is any constant. First thing you might notice is in this case, now theta is the parameter. And that's totally okay. We don't have to have t as a parameter. The second thing you might notice is it's also hard to solve for. Hard to solve for theta. Now, again, you might be thinking, well, no, it's just an inverse trig situation. But it's hard to solve for theta. Even if we used inverse trig, y would be messy. So we have to have something else to do to get a nice equation. And what that's going to end up being is, in general, what you end up doing in this situation, in this case, try to solve for cosine theta and sine theta, then use identity. Which identity? Our favorite trig identity, cosine squared plus sine squared equals 1. Okay. So what will this look like? I'd have x over a equals cosine theta, y over a equals sine theta. And if I substitute them into this equation, my identity, if I take these two and combine it with these, I'd have x over a squared. Careful with how it substitutes. Remember, the cosine squared means the whole quantity is being squared, equals 1. I'm just going to simplify this a bit. And then we'd have x squared plus y squared equals a squared if I multiplied both sides by a squared. So what do you have here? This is the equation of a circle with radius equal a and centered at the origin. And so that's what we're talking about. We're talking about when we have x equals a cosine, y equals a sine, we're going to get a circle. It's going to be centered at the origin. It's going to have the radius a. And in case you're more of a visual person, literally what I'm talking about is this, right? We all should be able to visualize that. That's going to be a. And we should be able to talk about the, taking that's negative a. We need to be able to talk about the orientation, again, the direction along this curve. So what's going on here? Let's just graph x equals a cosine, y equals a sine, with theta on the interval from 0 to pi. Okay, so what would that look like? We'd have the initial would be a comma 0. That's plugging in theta equals 0 into our equation. And the terminal would be negative a comma 0. So again, we know what shape it has, and now we know the initial points over here, a comma 0, and the terminal points over here, negative a comma 0. And so the only question is which half of the circle we have. I hope you can all see it's going to be 1/2 of our circle. And I hope when you think about how theta goes, because theta is oriented counterclockwise, we're talking about the top half of a circle with this orientation, with a counterclockwise orientation. Okay? So I'm not going to draw this out, but 0 to 2 pi. I don't know why I'm writing pi. 0 to 2 pi is the full circle. Make sure you're seeing that. That would give a full circle, again with the counterclockwise orientation. And what about something like 0 to 4 pi? So here it won't suffice to do our terminal initial point, but we would notice that we are going to get from 0 to pi, 2 pi, our full circle, and then we go around again. So then we go around twice the same circle. So it's 2 laps of the circle. Okay? That's what's happening because we have 2 full circumferences. Still with radius A. So, one more example, at least. So what about something like x equals a cosine theta, y equals b sine theta? So if the coefficients were equal, we had a circle. So what about x equals 4 cosine theta, y equals 3 sine theta? And we'll do theta for the zero to 2 pi, a full period of sine and cosine. So what happens here? So again, it's the same strategy. We'll try to solve for we'll try to solve for cosine and sine of theta. So we have cosine theta equals x over 4, sine theta equals y over 3. Make sure you understand where I'm getting this next equation from. The Pythagorean identity tells me that cosine squared plus sine squared equals 1. Therefore, just using substitution, I should have this. Now, before I even start simplifying this, some of you should be able to tell me what this is supposed to look like, what this is, a graph of this would be. Some of you might not remember everything from your honors pre-calculus class or your pre-calculus class or Math 3. What this is the equation of an ellipse. And in case you're having trouble remembering, these numbers, the A and the B here, if we're looking up, again, back at the top, the A and the B are representing the intercepts. For instance, on the x-axis, we're having a 4 and negative 4. And on the y-axis, we're having 3 and negative 3. So it's not a circle. It's an oval or an ellipse, or like I always end up drawing something that looks like a football. And again, it's this counterclockwise orientation. It's a counterclockwise orientation that's traveling this way, like we normally would do with trig. So, that's enough of the basics. I will say one more thing. What if I had x equals 2 plus 4 cosine theta and y equals 3 plus 4 sine theta? Okay, what's going on now? So the first thing I'm going to point out is that these numbers are still the same. Because those match, we have a circle. And you should be able to tell me the radius already, because that number is the radius. Okay, so the real question I'm wondering is, what did adding the 2 or the 3 here do? So we can put it into our standard form, start solving for cosine or solving for sine. I'll solve for cosine first. So x minus 2 over 4 was cosine. Y minus 3 equals 4 sine. Y minus 3 over 4 equals sine. And we have x minus 2 over 4 squared plus y minus 3 over 4 squared equals 1. Because again, it's sine squared plus cosine squared equals 1. So this number on the right side should always be 1. When you square this, don't FOIL. Do not distribute everything out. Whoa, 16. My hint. And so we have here, you multiply both sides by 16. So again, that's r squared. Oh, it is 4. Good, good, good. And you should remember that these reflect that the center is at 2, 3. It's what would make both of them equal 0, the x and the y. It's not a point on the circle. That's why plugging that in doesn't equal 16, in case you're thinking that. And that's right up here. That's the 2. That's the 3. So that's what adding numbers to these equations would do. All right, so that's enough. Try out the homework, and good luck. Thanks.